Hi, in this video, we would like to talk about continuity. Okay, so notice the graph of continuous functions has no gaps, holes, jumps, and or vertical asymptotes. Okay. Let us consider the situation that we have before is how we talk about the limit. When we say the limit x approach a of f of x equal to L, is actually tell me that I have a function f is from the left, as x approach a from the left, then the output that I have is equal to L. And as x approach a from the right, okay, the output is getting closer and closer to L. Okay. So in this case, the limit exceed. What if L is equal to f of a? Then in this case, meaning f of a is equal to L, then what happened to the functions? Now we could say that the function is continuous at x equal to a now. Okay. So this is about the continuity. Okay. So, okay. Then now we just found that if I want to talk about the function is continuous at a, then we could write down the limit x approach a of f of x equal to f of a then. Okay. Notice that definitions of continuous continuity at a point implicitly required three things if f is continuous at a. First of all, f of a is defined. What does this mean? It means that f of a is a number. Second, the limit f of a, the limit when x approach a of f of x exceed. Okay. So in this case, we could go back to the previous sections. Okay. So in this case right here, we could just evaluate the limit. If the output that we have is a number, then the limit exceed. Okay. If we have a piecewise functions, then for example, like this example number 5 here, if we have a piecewise function, and then if we would like to evaluate as x approach -5 from the left, the limit x approach -5 of f of x, then remember we have to apply, that means to take the limit, to evaluate the limit from the left and also from the right. If they both the same number, then again, in this case, the limit exceed. Then with the first and the second, then we also need to show that the limit x approach a of f of x is also equal to f of a. Then if we could show these three conditions, then we will say that the function f is continuous at a number a then. Okay. The following example is the idea is about this continuous function now. The first example, this one is actually if I have f of x is equal to x squared minus x minus 2 divided by x minus 2. And look at this function f. When x equal to 2, the function is discontinuous, right? Because again, we divide by 0. So in this case, why we say that this is a removable? The reason is if I factor the x squared minus x minus 2, then I have x minus 2, x plus 1. And then if we divide by x minus 2, then in this case, you will see that now we have a removable. Okay. So then the function is discontinuous at x equal to 2 now. Okay. And then to this problem right here, basically it will fail the first conditions is f of 2 is undefined. Okay. So therefore the function is discontinuous. The second example B right here is actually to this one right here. Why it is discontinuous at x equal to 0? Okay. First, the first condition is okay, right? Because f of 0 is equal to 1. Okay. So it's past the first conditions. Okay. So f of 0 is defined. However, in this case, you will see that the limit does not exceed because the limit as x approach 0, maybe from the left of the function f, you will see that basically what happened, the limit that we have as x approach 0 from the left, the output that we have is getting bigger and bigger. Okay. So in this case, the limit does not exceed. Okay. So therefore to this one, this example B is fail the second conditions. Then now let us look at the condition C now. That's been the problem, this example C. Okay. To this one, again, the first condition is f of 2 is actually equal to 1. So f of 2 is defined because it is a number. Second, the limit exceeds it is equal to this number. Okay. However, maybe let us try to see the limit, right? So again, to this one, the limit x approach 2 of this one right here, we could factor this is x minus 2, x plus 1 divided by x minus 2. Okay. Again, in this case, we will have the limit x approach 2 of x plus 1. Then now, if I evaluate the limit direct substitutions, I will have 2 plus 1, which is 3. Okay. So the limit exceed and the limit x approach 2 of f of x equal to 3. Okay. However, the third condition is actually failed the third condition now because the limit x approach to 2 of f of x equal to 3, not equal to f of 2. So to this example right here is actually, again, is this continuous at x equal to 2 now. Okay. Then now, let's see how do we actually work with the problem. Okay, We are going to use the definitions of continuity and the property of limit to show the function is continuous at a given number a. So what I need to do is I need to follow these three conditions to show that the function is continuous at x equal to a now. So then the first conditions need to show h of 1 is defined. Okay. Meaning I just need to evaluate h of 1. And then you will see that is 2 minus 3 divided by 1 plus 1. So it's equal to negative 1/2. So in this case, h of 1 is defined. Second, need to show the limit exceed. Right? So then I will have the limit t approach 1 of h of t, which is then we could use direct substitutions. Right? 2 times 1 minus 3 times 1 squared divided by 1 plus 1 to the power 3. So you will find that the limit exceeds and the limit is equal to 1/2. So now we go to the third condition now. So now we have the limit x approach, it is t approach 1 of h of t equal to negative 1/2. It is equal to h of 1. Okay. So now you will see that it satisfies all three conditions here. So we could say that here h is continuous at t equal to 1. And now let us look at our second example. Suppose I have a piecewise functions f of x equal to 3x to the power 3 minus 2x if x is less than 1. F of x equal to 2x squared minus 1 if x is greater than or equal to 1. Okay. Okay, so then now what they want you to do is the function continue as x equal to 1? We would like to circle the response and also justify your above answer using the three conditions definition of continuity. Okay, so what I need to show is I need to show these three conditions. Okay. Okay, so remember again, if you want to try it your own, then pause your video and then try it out, okay? Since this is a piecewise function, so, and then x equal to 1 is actually is the boundary, right? So again, check it out. So I have x equal to 1, okay? And then when x approach 1 from the left, okay, meaning when x is less than 1, then the function that I'm going to work with is actually, it will be 3x to the power of 3 minus 2x. X greater than or equal to 1, we are going to use the function 2x squared minus 1. Okay. However, when x is equal to 1, when x is equal to 1, we have to use 2x squared minus 1, this function to evaluate. Okay, keep that in mind, right? Piecewise functions. Okay. Then now let us work with the three conditions. The first conditions, I need to evaluate f of 1. So in this case, I'm going to work with the function 2, 1 squared minus 1. So in this case, I have 2 minus 1, which is 1. How about the limit? So again, since this is a piecewise functions, and then we are going to evaluate as x approach to 1. So therefore, in this case, I need to find the limit from the left and from the right now, right? Now on the test, what I would like you to do, I would like you to write down the function f, okay? In this case, right here, since we are using x approach 1 from the left, is 3x to the power 3 minus 2x. I need you to write down this to get credit, okay, on the test. Then use direct substitutions. So I have 3 minus 2. So again, it's equal to 1. Limit x approach 1 from the right. So I have the limit x approach 1 from the right, and is 2x squared minus 1. Direct substitution. So we find that limit from the left and the right of f of x equal to 1. So limit exceeds. And the limit x approach 1 of f of x equal to 1. Then now show the third conditions. Limit x approach 1 of f of x equal to 1 equal to f of 1. Okay. So based on these three conditions, we can say that the function f is continuous at x equal to 1. Then we go back to circle yes, okay, to finish the problem. Then now, let us look at the next example now, okay? Sometimes we have to have the kind of like to talk about continuous only from one side, okay? Then what is the conditions here? Sometimes we have a functions like f of x equal to square root of x, okay? So you will see that in this condition right here, or to this function here, then what happened when we talk about when x equal to 0? Okay. Now you will see that at x equal to 0, when we talk about the limit x approach 0 from the left of x of f of x, it doesn't make sense because we have nothing is from the left. Okay. So therefore, in this case, we don't know what it is. Okay. So therefore, but again, I know that the function basically start at x equal to 0. Okay. So then now what we could do is we could talk about the one side continuity now. So if I want to have the limit x approach to 0 from the right of f of x, as x is getting closer and closer to 0, okay, from the right hand side, then you will see that what happened to the functions. The function is going to 0. Okay? So therefore, in this case, this is the reason why we need to have this definition right here. Okay. Okay. So a function f is continuous from the right at a number a if the limit x approach a from the right of f of x equal to f of a. And f is continuous from the left at a if the limit x approach a from the left of f of x equal to f of a. Okay. So now the definition of continuous on an interval, then a function is continuous on an interval if it is continuous at every point in the interval. If f is defined only on one side of the endpoint of the interval, we understand continuous at the endpoint to mean continue from the right or continue from the left. Okay. Just like the situation that we have here. And now let us look at the following example now. I'm going to use the graph of this function f. Okay. To work on a and b, what is a? A is from the graph of f, we would like to state a number at which f is discontinuous and explain it why. Okay. When we try to explain, then we could use the three conditions to help us to do this. And B, for each of the numbers stay in part A, determine whether f is continuous from the right or from the left or neither. Okay. Let's see how we actually work on this problem. Okay. Now maybe let us screen through the graph from left to right. Okay. Then you will see that the first discontinuous occur at x equal to -4. So then we could say that at x equal to -4, we found that f of -4 is not defined. Okay. This is the reason why at x equal to 4 is discontinuous. Then now, let's check if the function is continuous from the right, from the left, or neither. Okay. So in this case, how do I know that it's from the left or from the right or neither then? Then we have to check it. The function approach -4 from the left. In this case, we have an open, meaning f of -4 is not defined. Okay. So therefore, it's not continuous from the right. Then now, how about from the left? Same thing. From the left, again, it's open here. So therefore, it's not continuous from the right, from the left. So therefore, in this case, it will be neither. Okay. Then let us look at another situations. Then now, probably is -2 at x equal to -2 then. Okay. Then to this one, the first conditions, f of -2 is defined. That means it's okay because f of -2 equal to this number right here. However, the limit does not exceed. So you failed the second condition. Again, why is does not exceed? From the left is this number here. From the right is another different number, right? Okay. So therefore, the limit does not exceed. And then now, let's see if f is continuous from the right or from the left now. Okay. So in this case right here, then let's check. So the limit from the left, we have an output. So meaning the limit exceed and the limit equal to this number. Okay. And also f of -2 equal to this number. So meaning the function is continuous from the left. However, from the right, the limit exceeds the limit equal to this number. But f of -2 is not equal to this number. So meaning the limit exceed, but f of 2 at this right here, f of -2, right, does not exceed, okay, or undefined. So then in this case, I will say that f is continuous from the left then. Okay. Okay, now maybe you could pause the video and then check it out the rest of the graph now. Then my next number, it will be 2. Okay? Now, not 0, right? Because the function is continuous at x equal to 0 from the left, from the right, and also f of 0 is defined, right? The limit exceeds f of 0 is defined, and also the limit is equal to the f of 0. Okay, so therefore, the function is continuous at x equal to 0. Then how about 2? At x equal to 2, then the first f of 2 is defined. We have this output right here. Okay. However, limit does not exceed. Okay. Again, you see that now. Right now, maybe you could see that if we have a jump, then the limit does not exceed. Then let's check it out. Is the function f is continuous from the right, from the left, or neither now? So then from the left, we have this open. So it's not continuous from the left. Okay. From the right, this is okay, right? We have a solid right here. Okay. Then now the next number will be 4. Again, f of 4 is defined here. Right? This is the output. However, limit does not exceed. Okay. So that make the function discontinuous at x equal to 4. Then now, to this is mean that probably the function is keep going down as x approach 4 from the left. And now, how about from the right? Okay, so then in this case, we will have this is from the right. So it's okay, right? We have this. Then probably in this situation right here, we may have like the vertical asymptotes. That is from the left now. So now let's look at the following figure now. If f and g they are continuous at a and c is a constant, then the following functions are also continuous at a. Okay. The sum of two continuous functions at, again, the sum of f and g, the difference f minus g, a constant multiply f multiplied to g, and number 5 is f divided by g if g of a not equal to 0. Okay. Then let's see how do we actually prove the theorems. Okay. So when we try to prove this theorem right here, f plus g is continuous at a, what we need to do first, we need to start with the given conditions. Okay. This one is telling me that f and g, they are continuous at a. Now this is kind of like a procedure to prove a theorems. Okay. We start with the given conditions. So in this case, if we know that f and g, they are continuous at a, what does this tell me? Okay. Suppose f and g are continuous at a. This tell me that the limit x approach a of f of x equal to f of a. Also, limit x approach a g of x equal to g of a. Okay. And also, if f plus g is continuous at a, what does this tell me? If the limit x approach a of f plus g, okay, if equal to f plus g of a, then it will tell me that the function f plus g is continuous. At a then. Okay. So when what I need to do is this actually is our goal. I would like to show that. Okay. Then let us go back to the proof now. Okay. So then we would like to start with the limit x approach a of f plus g of x. Then we know that to this one is mean f of x plus g of x. Right? And the limit law tell me I will be able to rewrite this into the sum of two limits. And now the limit x approach a of f of x equal to f of a. The limit x approach a of g of x is equal to g of a. Then we could rewrite this to f plus g of a. Then now we could make the conclusion now. Since limit x approach a of f plus g of x equal to f plus g of a, the functions f plus g is continuous at x equal to a. Okay, now this theorem also tell me that the following type of functions are continuous at every number in their domain, like polynomial functions, rational functions, root functions, trig functions, inverse trig, exponential function, log. Those are the functions that they are continuous in their domain. Okay. And particularly the polynomial function, exponential functions. Okay, polynomial function, something like this, right? Exponential functions is something look like this. And then the sine functions, the cosine functions, the absolute value of x. Okay, you will see that they are continuous everywhere at every value of x. Since the domain of polynomial function, exponential functions, sine, cosine, and absolute value of x, all real numbers. Okay. And of course, we could use the theorems here to show us that too. Now, one thing about this is, what if I want to show that one of these functions, okay, they are continuous at everywhere, okay? Then now I need to have another theorem to help us to do this then, okay? So to this theorem is tell me that the limit x upon a of f of x equal to f of a if and only if limit h upon a of f of a plus h equal to f of a. Wow, what is this telling us here? Okay. Now we have a functions. Okay. And then we have this the distance between A and A plus H is equal to H. Okay, this is the distance between them. So then now, let's see here. If H oppose 0, you will see that if H oppose 0, if the function is continuous, then what happened? When H is getting closer and closer to 0, meaning this point right here is getting closer and closer to this point, right? So therefore, as X oppose 0, what happened to f of A plus H? It actually is equal to f of A then. Okay. So then this is kind of like the idea about this theorem right here. Okay. Then let's see how do we use this theorem right here to help us to show that the function psi of x is continuous at every point. Okay. So what we need to show is we would like to show that the limit h oppose 0 of psi of A plus H equal to psi of A. If I could show that, that means, again, A is any number, right? So that means the function is continuous, okay, everywhere now. Okay. So let's see. We are going to start with the limit x oppose 0, h oppose 0, psi of A plus H. Okay. Then maybe I should review psi of A plus B is equal to psi of A cos of B plus psi of B cos of A, right? Okay. So now we could actually use this to help us to rewrite psi of A plus H. So it will be psi of A cos of H plus psi of H cos of A. And now using the limit law, we are going to rewrite this into the sum of two limit. And of course, psi of A is a constant. Cosine of A also a constant. So we could take out the psi of A out of the limit. And now we could use direct substitutions. Then cosine of 0 is 1. Sine of 0 is 0. Then my answer is psi of A. Okay. So now you could say that sin limit h oppose 0 of psi of A plus H equal to psi of A. the functions f of x equal to psi of x is continuous at every point then. So now another theorem is tell you that f of x is continuous at L and the limit x approach a of g of x equal to L, if this is okay, if this is true, then when we take the limit x approach a of f of g of x, composition of function, right? We could actually just evaluate the limit x approach to h approach a of g of x first. Okay. And then after we get the result, then we are going to evaluate at f. So therefore, in this case, the limit x approach a of g of x equal to L. So then the result will be f of L then. Okay. Let's see how we use the theorem to help us to work on number 6. Okay. So again, this is a composite functions. Then now what we could do, we could actually just take the sign of the limit x approach pi of x plus psi of x. Okay. And the domain of x is all real number, so we will be able to calculate direct substitutions. So I will have this is pi. Okay. And again, we just know that the psi functions, again, the domain is all real number, meaning is also continue at x equal to pi. So we could evaluate psi of pi as well. Okay. Okay. Then what is psi of pi equal to? Then if you don't remember, then we could actually grab the function, right? Okay. Then, of course, one thing you have to know that this is 0, this is pi, this is 2 pi, and this is a pi over 2, this is 3 pi over 2, and then the function is bounded between -1 and 1. And psi of pi is equal to 0. Okay. So then my answer will be psi of pi, which is equal to 0 then. Okay. Then now, let us look at our next example now. It said that for what value of the constant c is the function f continuous on the interval between -infinity to infinity, meaning we are looking for all real numbers, then the domain of this function f. Okay. Then now, to these functions, again, you will see that it's really similar to one of the problem that we did earlier is related to the limit, right? Okay. But this will be slightly different. To this problem, we only talk about the limit exceed at x equal to 2. Okay. However, to our problem here, we need to work it out. The function is continuous everywhere. Okay. Then let's see how we actually work it out this problem now. Okay. Now, first of all, let us look at the piecewise function we have here. The piecewise function basically is, again, at x equal to 2, as x less than 0, or less than 2, the function will be cx squared plus 2x, which is polynomial functions. As x greater than 2 is x to the power 3 minus cx. Again, it's polynomial functions. Then we know that polynomial functions, basically, the domain is all real numbers. Okay, so then we could actually say it here. Then since cx squared plus 2x and x to the power 3 minus cx, they are polynomial functions. F is continuous on the interval negative infinity to 2 union with 2 to infinity. Then now the trouble is, or maybe I should say that what we need to do is actually we need to show that at x equal to 2, if the function continue at x equal to 2, then the function will continuous on the interval negative infinity to infinity then. Okay. Then now we could say that suppose the function f is continuous at x equal to 2, then f is continuous on the interval negative infinity to infinity. Then now, let's see, if f is continuous at x equal to 2, then we will say that the limit x opposed 2 of f of x is equal to f of 2. Then now, if this is the case, what I need to show is, again, the limit exceeds, right? Maybe I should say that if f is continuous, that means the limit exceeds. Okay, so if the limit exceeds, then we will say that the limit x opposed 2 from the left of f of x must equal to the limit x opposed 2 from the right of f of x. Okay, based on this. Then, again, we are going to work with the piecewise function now. The limit x opposed 2 from the left. Okay. So in this case, if the limit opposed 2 from the left, meaning we need to work with this function here. So I would like to write down is cx squared plus 2x, which is equal to limit x opposed 2 from the right of this function. Okay, from the right, it must be this one. So I would like to work with x to the power 3 minus cx. Okay. And now, we are going to work with, again, direct substitution, right? I don't need to write down the limit notation now. So we could have this will be c times 2 squared plus 2 times 2 is equal to 2 to the power 3 minus c times 2. So I have 4c plus 4 equal to 8 minus 2c. Then I will have 4c plus 2c. We just need to solve for c. Equal to 8 minus 4. C is equal to 4 divided by 6. And we are going to simplify. So, which is equal to 2 over 3 now. Then we can make the conclusion now. If C equal to 2 over 3, F is continuous on the interval negative infinity to infinity. So the last topic that we would like to talk about in this section right here, continuity, is I would like to introduce the intermediate value theorems for continuous functions. Okay. So let's see what is this theorem about. It said that if f is continuous on the interval ab, and v is any values between f of a and f of b, then there is a number c between a and b, so that f of c equal to b. If c is a number between a and b, then so that f of c is equal to b. That's it. F actually takes each intermediate values between f of a and f of b. Then. Okay. So then maybe let us try a couple continuous functions, right? To see if this is probably true, okay? And then now you will see that there's a number c right here. Then you will see that the output is v, and this v is always in between f of a and f of b. Okay. You could grab different functions and then to try it out. Okay, it's always work. Then now, one way to use the intermediate value theorems is try to find roots of the functions. Okay, and sometimes to solve the equation as well. So first of all, I don't know if you know what roots are. Actually, we could talk about this root right here. Okay, now most of the time is we call this a 0. Okay, or sometimes you refer to the x-intercept. Okay. This is actually is about that's mean the name of roots. Okay, it could be 0, it could be x-intercept. It's just different textbook. They name it differently then. If f is continuous on the interval ab, and f of a and f of b have opposite sign, one is positive, one is negative, right? Then 0 is an intermediate values between f of a and f of b. Okay, so c will have a root between x equal to a and x equal to b. Okay, so what is this? How is this look like then? So we could consider the situation here. So right now I have a continuous functions. This is a, this is b right here. Okay. Then you will see that in this case, this is my f of a. And this will be my f of b. So now f of A negative, f of B is positive. And you will see that there is a number C where f of C is equal to 0. Right? Okay. So this is kind of like the idea here. So now if I want to use these intermediate values theorems to show that there is a root of the given equation in the specific interval. So what do I need to do? Basically, what I need to do is I need to show that, okay, the function, that means I need to show something like f of 1. If f of 1 is positive, then f of 2 must be negative, okay? Then I will be able to show that there must be a number in between 1 and 2 that make f of c equal to 0 then. Or f of 1, if f of 1 is negative, then f of 2 must be positive. Okay, this is the idea. Okay, but now, since this is an equation, so how do I actually work with that function f, right? Then one way to do this is, okay, we are going to make this, okay, kind of like solving equation, right? We are going to move everything to one side. Okay. Then now, if we do this, then we are going to let f of x equal to psi of x minus x squared plus x naught. Okay. Then if it is, we set it equal to 0, then now what we want to do here is we would like to find the x-intercept, isn't it? Or root. Yeah. Then we could work with this. Okay. Okay. So then first of all, let's check it out. Okay. Now you see the first condition is the function must be continuous. Then let's check it out, this function right here. So you will see that the psi of x is continuous functions. X squared is continuous functions. X is also continuous function. That means it's continuous everywhere. So therefore, in this case, we could say that f is continuous on the interval between negative infinity to infinity. Okay. So this implies f is continuous on the closed interval 1, 2. Okay. Again, why we need to work with the closed interval? Because based on the intermediate value theorem, this is one of the conditions that we need to have. And now let's see. F of 1 is psi of 1 minus 1 squared plus 1. So we choose psi of 1. Okay. And now we know that the angle 1 is in quadrant 1. Okay. That means psi of 1 is positive then. Okay. Or you could actually look at the graph. Okay. So 1 probably is a number before pi over 2, right? So again, you will see that is a positive now. Okay. Then how about f of 2? So I have psi of 2 minus 2 squared plus 2, which is equal to psi of 2 minus 4 plus 2. I will have psi of 2 minus 2 then. Okay. Then now, how do I know that this is negative or positive? Okay. Now, one thing that I know, the psi functions is always bounded between -1 and 1. Okay. So the maximum number to this psi of 2, okay, maybe it will be the maximum is 1. So if I have 1 minus 2, it is negative, right? So therefore, in this case, I know that f of 2 must be negative. So if this is the case, then we could say that by the intermediate value theorems, okay, that exceed a number C such that f of C equal to 0, where C is in between 1 and 2. Where C is the root of the equations. Okay, so that's it for this long lecture now. Okay, thank you.